Hello everyone, I am Professor Anish Vora and I welcome you all in this video lecture. In this video lecture, we'll study about covalent bonds. In case of crystalline structure of semiconductor, we have seen that it is the tendency of each atom to complete its outermost orbit by sharing, by gaining or by losing valence electrons. Neighboring atoms share electrons with central atom, and central atom has 8 valence electrons. These electrons do not belong to any one atom. The electrons are attracted equally by positively charged core. The poles are equal and opposite, hence they are bonded together. This type of bond is called covalent bond. Now let us see the crystalline structure in detail to understand the covalent bond. We have central core and we have neighboring atoms. We have nucleus and we have filled orbits. Each atom has 4 valence electrons in their outermost orbit. But now we know that neighboring atoms share 1 electrons each with the central atom. So now we can see that central atom has 4 its own valence electrons and 4 are shared valence electrons with the neighboring atom. These valence electrons of central core are making covalent bond with valence electrons of neighboring atoms, and this structure goes on. So these are valence electrons, and the dotted line that is known as a covalent bond, and we have positively charged core. So we can see that valence electrons are tightly bound with the nucleus, and that is why there is no free electrons available at absolute zero temperature in case of germanium and silicon. So semiconductor material behave like insulator. In case of pure germanium and silicon, at absolute zero temperature, there is no free electrons, as just we have discussed, and that is why pure silicon or germanium behave as an insulator. But in case of semiconductor material, we know that forbidden energy gap is quite small. Even at room temperature also, heat is imparted to valence electrons, and some of the valence electrons gain the energy required enough to cross the forbidden energy gap and to travel to conduction band. Now let us see the valence electrons gain the energy and becomes free. It travels to conduction band as a free electrons, but when free electrons move to the conduction band, it leaves a vacant position in the covalent bond, and that is known as a hole. So this pair of electrons and hole is generated when heat energy is applied and some of the covalent bonds are broken. The generation of electron and hole, that is a pair, is known as a thermal generation. We can see in terms of conduction band and valence band also. We have valence band and we have conduction band. In case of semiconductor material, the forbidden energy gap is quite small, and we have valence electrons in the valence band. When heat energy is applied, even at room temperature, covalent bond between valence electrons break and valence electrons travel to conduction band and becomes free electrons, leaving behind a hole in the valence band. So this pair of free electrons and hole is generated because of thermal energy applied to the valence electrons. So these are known as free electrons, and the position become vacant, that is known as a hole in the covalent bond. If temperature increase, then some more covalent bonds are broken, some more valence electrons become free, they travel to conduction band and act as a free electrons in the conduction band. Conductivity in the conduction band goes on increasing, or resistivity of the semiconductor material decrease with the increase in the temperature. That is why resistance temperature coefficient of semiconductor material is negative, because resistance decrease with the increase in the temperature. So this way, with the help of heat energy, some of the covalent bonds are broken. Valence electrons becomes free electrons and travel to conduction band, leaving behind holes. These holes are also a charge carrier. Like electrons, the movement of holes that can be also act as a flow of charge, similar to the flow of electrons. Thank you for watching my video. Keep watching. Thank you very much.